I didn't quite know what to do about these explicit calculations. I decided to do the first one, problem 5, semi by hand, and then I would make a computer program to compute the value, the critical value, given n, to some predetermined decimal places, and program that in Maple. So what I'm going to do now is to make it almost by hand, but of course doing the numerics in Maple. And the first thing I did was to write up the formulas we need to use. So I took the expansion from formula 5.7 of the L function, and then applying formula 6.8, I ended up doing this. Now what we need is to say we do it to 4 decimal places, and that means that we need to use the remainder, the formula for the remainder, and that's on page 96. Now that's a little weird. I think this should be square root n. So they actually only did it for n here being equal to unity. The bound for each term is still given in the proposition 13, independent of n. So I'll just write this up as I think it is, and then I will make break, control it, check it, and then solve it in Maple. That's square root n mark, isn't it? Like up here. So that was collecting the formulas I hope are all we need. I really expect this expansion to be sufficient. I started doing what I said I would. Computing this temporary term. I'll just make it a little bigger for you, and then solving for m, how far do we need to go to get it with 4 decimal places, and that was term 14 we need to have. So I used the first terms here. This gives naught, this gives unity, of course. Then I believe that this is -1, so I subtract it. And then I wind up with this sum and just verified that the next term was much smaller. So never mind about that. Actually, going to n equals 3, I found out that we need to take all terms up to number 31, up to n equals 31, and I don't have all the numbers. I need to do that, but before embarking on that, then I will, first I'll have lunch, and then I will check this result with the first 5 decimal places, which should be the same. You see, Paris can actually work all this out exactly, as you've already seen, I believe. So that's the plan for the next hour or so. it turned out I had simply forgotten a term. It took quite a while to find it. I checked all the coefficients and yeah, but I'd simply forgotten a term. The problem of how to handle the next series to get all the terms up to number like we'll get 29 is I can either do it by expanding the series or by using one of the problems. I guess it was problem 3, where we had a formula for computing I think I'll make a compromise. So I'll, from the series expansion, get all the prime powers, or the value of all the primes, I think is better. Yeah, the value of the primes, and then use the recursion formula to get the prime powers. I think that's what I'll do. So this is 5th, maybe that's what confused me. Oh yeah, that was exactly why I missed it. Because the Legendre symbol of n with respect to 2 vanishes, but with respect to 5 gives -1, so it's +2/5. All right. I don't know where I got the plus from. Oh, that was from the book. All right. So we take the product formula for the n series, and let's take the prime powers of 3. So we get -3, 9 to minus s, and then a squared plus, but that's 81, that's not really good. And then 2p = 5. Actually, we don't need this because this will vanish anyway. So let's start with 5. So we get -2 times 5 to minus s. And then, 25. It's -25, and then the double product, that's -4. So I believe it's -29, 25 to minus s. We need to check this with the recursion formula. Then p = 7 gives 49. P = 11 gives nothing. P = 13 gives 6. 13 to minus s. P = 17. That's -2 to +2. I better write plus. 2 times 17 to minus s. This is what they did. Then 19 gives nothing. Then we have p to 23. '25, 27, then 29. And they are This is equivalent to 3 modulo 4, so that gives nothing, only the square. So this is the only new guy we get. And the square root is plus minus 5 plus minus 2i, and plus minus 2 plus, plus minus 2 plus minus 5i. There should only be 2 square roots, so what the hell? Oh, that's the prime ideals dividing it. So we need to find one which is equivalent to, now what should it be equivalent to? I think it should be equivalent to 1 modulo 2 plus 2i. We'll just need to check that. Now that's a little difficult. So I'd very much like to subtract. Oh, we take minus 5 plus 2i, and then we add 4 plus 4i. No, we do not. 6 plus 6i, and that's equivalent to 1 plus 8i, and 8i is equivalent to 0, so that's equivalent to 1. So this guy will do. And that means that our factor is minus 10. Now we should be able to take all the products that come. 3 falls out. So there are no prime powers, so we only get the products. That's 60. Oh, there's really nothing new. All right. So it's just about making a break and writing this into Mabel and see that it doesn't fit. All right, guys. I collected the terms, and the only new one was the prime 29. And it agrees. It didn't first because I wrote 2/5 here. And I've computed the Legendre symbols by themselves. Of course, when making the program, I will have to compute each coefficient and put it in an array. So and I don't really have a verification of the products we get. So it wasn't very helpful regarding the algorithm I need to program later in Mabel here. But at least this problem is solved. We get, I required 4 decimal points, and that's what we've got. I actually had expected something better, I'd expected it to fit better. So maybe I've made a mistake on one of the last terms. But never mind. In principle, I've got it.